There's another unit that we're going to want to be able to describe. That unit is the units for temperature. Temperature, we're just going to say, is something that we measure with a thermometer. That's a pretty good way to get us going. And we'll maybe get a little bit more insightful in our definition once we start talking about actual gases and thermochemistry. For now, this is a pretty good definition, and originally this is all anyone really knows or notices about temperature. And the reason we care is because many properties happen to change with temperature, including things like reaction rates. So we're going to need some temperature scales in order to perform these temperature measurements on our thermometers. The first scale that's come up with is in 1724 by Daniel Fahrenheit. So his scale, he makes 100 degrees Fahrenheit the temperature of the human body. We've adjusted the scale a little bit, so now it's 98.6. And 0 degrees Fahrenheit, he makes this brine solution, this concentrated salt water. And when he makes it really concentrated, the temperature at which it freezes, he defines to be 0 degrees Fahrenheit. And now if you divide this scale up into 100 pieces, so you have our units of Fahrenheit, and then you keep counting up as you raise the temperature. Once you start noticing water boiling, you have reached 212 degrees Fahrenheit. Also note that when you're at 32 degrees Fahrenheit, that was the temperature at which water froze. So this is quite a bit lower than the temperature needed just to freeze regular water without the brine solution. Well, another scale that's developed in 1742 is due to Anders Celsius, the Swedish astronomer. So his scale, he starts out where water freezes. He actually flips this around. So he starts out at 100 degrees Celsius for where water freezes and 0 degrees Celsius for where water boils. We've decided it's more convenient to count up instead of down while we're increasing the temperature. So we go ahead and use 0 degrees Celsius for where water freezes, 100 degrees Celsius for where water boils. This is a little bit better for scientific work. Turns out to be hard to construct this brine solution in order to get the same temperature scale in your lab that someone else has in their lab. But there's still an issue, which is that, depending on the pressure, water might freeze at a different temperature. So this is still a little bit ambiguous here. Our last improvement comes in 1847 due to the British physicist Lord Kelvin. And for reasons that we will see when we begin to discuss ideal gases, he has some insights into a temperature which is the lowest possible temperature that there can be. And it turns out that if you take Celsius units and you count backwards from the temperature at which water freezes, that when you count backwards 273.15 units, you reach that coldest possible temperature. So in a Kelvin scale, that's defined to be 0, absolute 0, the coldest temperature there can be. 273.15 is the temperature at which water freezes. And then all the other temperatures are also shifted by that 273.15 quantity. So the temperature at which water boils is 373.15 Kelvin. And the size of these kelvins is the same as the size of a Celsius. So the amount that your thermometer rises because you've increased its temperature will be the same in the Kelvin scale as in the Celsius scale. Mathematically, this is how you're going to convert between these two scales. In order to get into the Celsius scale from the Fahrenheit scale, we have different size of unit, so we need this factor here. And we also have a different starting point, different freezing point for water, for example. And so we need to shift the scale by that difference and then change the size of our units. As an example, if we wanted to convert the human body temperature of 98 degrees Fahrenheit into Celsius, So we would take 98 minus 32 and then multiply by 5/9, and we get 37 degrees Celsius as the human body temperature. Now if we wanted to take that 37 degrees Celsius and convert it into the Kelvin scale, what we have to do is we have to offset it by that 273.15. So we add those together, we get 310 Kelvin. This is the human body temperature in kelvins. Now note here that a change in Kelvin is going to be the same thing as a change in Celsius. So for example, if we have our thermometer marked off in Kelvin and our thermometer marked off in Celsius, then in order to translate this Celsius thermometer into kelvins, we'd have to add 273.15 to this, and we would get 373.15 kelvins. In order to translate 0 degrees Celsius into kelvins, we would add 273.15, get 273.15 kelvins. But the difference between these is the same in both cases. Since we would subtract these numbers, we would wind up subtracting the 273.15 offset that both of these numbers include. And so when we take their difference, we get 100 kelvins, just like when we take the difference over here, we get 100 degrees Celsius. But if we just had 100 degrees Celsius here on this thermometer, that's not the temperature in kelvins. That temperature is 373.15. So whenever there's two temperatures that we're taking the difference of, then it's the same. When we're just considering one single point on our thermometer though, then that's where we have to use our conversion equation.